Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we cover all things Gen Chem related. On this video, we'll be learning about electron geometry and how we use it to predict the structure of these molecules. Let's get started. If you've been following along in this progression, we learned how to do Lewis structures back in chapter 9. Well, in this chapter, we're going to be learning how to take those 2D flat structures and how to make them into three-dimensional structures. Well, why is this important? So let's think about something that affects us on a day-to-day basis. So when we taste things. Now, the taste of food depends on the interaction between food molecules and the taste cells on your tongue. The main factor that affects that interaction are the shape of the molecules and the charge distribution within those molecules. The food molecule itself must fit snugly into active sites of specialized proteins on the surface of the taste cells. When this happens, changes in the protein structure cause a nerve signal to be transmitted. Now, when we think about things like sugar and artificial sweeteners, well, sugar molecules fit into a specific active site that's found on your tongue. And these molecules have a certain configuration to them that allows them to enter into this active site and then cause the ability to be able to have that taste sensation. Well, artificial sweeteners have a very similar structure, which allows them to simulate that same process where they're able to bind to those same receptors and generate that same response. So again, the idea of how the structure is made really does impact what properties are going to be affected on the outside. So the big thing we want to remember is that the structure determines the properties. The properties of a molecular substance depend on the structure of the molecule. The structure includes many factors such as the arrangement of the atoms, the bonding between the atoms, whether it's ionic, polar, or covalent, and then the overall shape of the molecule. Now, the bonding theory is going to allow us to predict the overall shape of the molecules based on the number of electron groups that are found around the central atoms. Now, we're going to be distinguishing between things like the electron geometry and the molecular geometry as we get later into this chapter. But the molecular geometry itself is going to tell us the three-dimensional shape of these molecules. And the shape that we're going to be describing really does relate to the geometric figure that it's simulating or imitating. When we're predicting these shapes, we're going to be looking at the corners or these positions that are surrounding that central atom to be able to define what that geometric figure is. And each of these figures that we're going to be creating are going to have characteristic bond angles associated with them. Now, Lewis theory allows us to predict the electron groups that are found within a molecule. And so remember, when we're doing this process in this chapter, when we're counting these electron groups, we're going to be looking at the regions of electrons that are there, not just the individual electrons that are there. Now, there's going to be regions that are those that are shared between atoms. So those are like your bonding regions. And then there are also those regions where there are those lone electrons that are found on a central atom. So again, notice I'm saying regions, not pairs. As we're doing our counting, we're going to be counting each bonding pair, whether it be a single bond, a triple bond, or a double bond, as a region. And each lone pair will be counted as a region. So we can use this theory to help us to predict the molecular shape of these molecules. Now, what Lewis theory tells us is that these electron groups, remember, they're negative, and so they don't want to be around each other. So they're going to orient themselves so that they are as far as possible from each other and repel one another. And this idea can now be extended to predict the overall shape of these molecules. It's going to help us to predict the overall position of the atoms surrounding the central atom. And then ultimately, the goal is to minimize the repulsions that are happening between these negative electron regions. So the theory that we're going to be using to help us predict these shapes is called the VSEPR theory. And VSEPR simply stands for valence shell electron pair repulsion theory. And in this theory, we're going to be accounting for all the electron groups that are surrounding the central atom. And then the resulting geometric arrangement that we see is what's going to allow us to declare what shape we are dealing with, and ultimately think about the overall bond angles that are present as well. So you can see here in this picture here, if we had something that had 3 electron groups surrounding a central atom, well, those electron groups want to get as far away from each other as possible. That repulsion is going to take place. And so the best configuration for these 3 electron groups to be away from one another is by making a triangle. And so what we're going to learn as we're looking at this shape, this overall triangle that's being created, The characteristic bond angle that's associated with that would be 120 degrees if these all were the same atom surrounding that central atom. So I mentioned it before, when we're doing this, as we're trying to predict these shapes, the main thing we're going to have to do first is not only have the Lewis structure in our presence, but then have to count the electron groups that are present. And so the electron groups that we're going to be counting are our lone pairs and the bonding regions. Again, notice I'm saying regions, not pairs. When we're counting, each lone pair that's on just the central atom will count as a region. And each bonding area, whether it be a single, double, or triple bond, will count as another type of region. So if we look at this molecule here, again, focusing only on the central atom, the nitrogen, we would have one lone pair, and then we would have 1, 2 bonding regions. Okay, so again, notice even though this is a double bond to the left, that's still counted as one region. So overall, in this molecule, on that central atom, there are 3 electron groups or regions. Well, that number 3 is going to ultimately dictate the shape that we're going to predict that it would take on. And what we're going to learn when we're predicting these electron geometries, there's only 5 different orientations that we can have, okay? When there's 2 electron groups, 3 electron groups, 4 electron groups, 5, or 6. So again, what we're going to be doing first is predicting what's called the electron geometry of the molecule. And I've written out a little schematic here that you really want to remember as you are doing this. Our progression when we tie in chapter 9 information in chapter 10 is going to go as follows. If you're not given the structure of a molecule, your first objective is to draw the Lewis structure. If you don't remember how to do that, go back to my chapter 9 videos and you can see how we go about drawing Lewis structures. That's the 2-dimensional flat structure. We then are going to count the number of lone pairs that are present, as well as the bonding regions. Remember, a bonding region is considered a single bond, a double bond, or a triple bond that's connected to the central atom. And again, that count, we're only looking at the central atom, not all the lone pairs that are found elsewhere. From there, once you've counted your electron groups, you can determine the electron geometry. The electron geometry is the shape that all the electron regions that are found around that central atom will make. We will then learn how to go from the electron geometry to the molecular geometry, and I'll talk about that more in a later video. But the molecular geometry simply is the shape that the atoms themselves, the molecule itself holds despite the lone pairs. And then from there, we'll be able to determine if something is a polar molecule or not. So that's your progression, okay? So if one step is missing, go back to the beginning and be able to do your progression. Now, if you're asked to determine the electron geometry of something, remember there's only 5 options for you. Something if there's 2 electron regions, 3, 4, or 5, or 6, okay? And so we're gonna go through each of these. Now, the beauty of this when you're dealing with Lewis structures that may have resonance structures that exist, regardless of how you have drawn it, you should end up with the same electron geometry because again, when we're counting those bonding areas, we're counting a single bond or a double bond as a region. And so if you've drawn them properly, regardless of which one you are exploring to be able to determine the electron geometry, you should still get the same answer. Okay, so first up, the first type of electron geometry that you may have is a linear geometry. And so that word linear implies that we're making a straight line. So this linear geometry is going to take place when you're dealing with 2 electron groups on that central atom. Now remember, when you're predicting this, you never want to make the prediction solely off of what you've drawn as the Lewis structure. You have to count those regions, lone pairs, bonding regions, and then you can determine what the shape is. If there are 2, like in this camp's example with BE, where there's only 2 bonding regions surrounding the central atom, no lone pairs. So we would say 0 lone pairs, 2 bonding regions. In this case, anytime we have a total of 2 electron groups, then the shape would be linear. And this happens because if we have 2 things that are trying to orient themselves as far away from each other as possible, well, then they'd want to make a straight line and create an angle of 180 degrees. Okay. And so you can see this as an example in both BeCl2 or in carbon dioxide. Again, when you're counting here, notice again, 0 lone pairs, 2 bonding regions. Don't count that as 4, because if you count 4, that may imply a different shape. 1 region, 2 region, okay? So the shape would be linear. And you can see with this balloon field model what the actual atoms might look. Again, we're making that 180-degree orientation. All right, up next, what happens when we have 3 electron groups surrounding the central atom? Well, we learned before, when you have 3 things surrounding that central atom, they're going to get as far away from each other as possible, and the shape that they're going to make is going to be a triangle. So again, don't try to predict the geometry off the Lewis structure, the shape that you've drawn. You have to actually count, and then you pair it or align it with the geometry we know that it takes. And so when we have, like in this example of 0 lone pairs and 3 bonding regions surrounding the central atom, 1, 2, 3, 3 bonding regions is going to create a shape of a triangle. That's a flat triangle. So the name of this is trigonal planar, okay? Trigonal planar. And the orientation, the bond angle will be 120 degrees, okay? And again, you can see the space-filled model here. All right, now we're getting up to the next one. What happens when we have 4 electron groups? Well, when you have 4, a lot of you may be thinking that perhaps 90 degrees is about as far as we'll be able to get these atoms from each other to make them as far away from each other as possible, prevent that repulsion. However, when you do 90 degrees, you're basically saying it's still a flat molecule. We can actually take advantage of the space that's in front of the plane, so like if it's coming out at you, or the space that's behind the plane, like if it's coming back towards me. And by doing so, that allows us to actually expand the angle that these atoms can have between them. So rather than actually making a square, like you may predict here, what the shape that they're going to end up making is a shape that's known as a tetrahedron, or a 4-sided pyramid. And so the name of the electron geometry for something that has 4 electron groups is tetrahedral. So 4 is tetrahedral. And so you can see in this example here with the carbon, we have 0 lone pairs on the central atom. Again, we're not looking at what's on the fluorine. And then we have 4 bonding regions. And so this shape, as you can see in the ball and stick model shown, is no longer flat. And by making it no longer flat, we can increase the bond angle up to 109.5. Well, now when we draw this, we have to think about how we're drawing it, because we want to be able to indicate the fact that this one looks like it's coming out at you, and this one looks like it's going away from you. And so how we do that when we're drawing these, we end up showing this with a wedge and a dashed line when we're drawing these. And those other 2 atoms would be shown with straight lines indicating that they're in the plane of that molecule, okay? So again, 4 electron groups is called a tetrahedron. Again, you can see this if I were to put that, the C and then the H here. These H's represent the corners of that pyramid. And so you have one coming out at you, one away from you, and then 2 that are in the plane. And that angle is 109.5 degrees. All right, moving it forward. Next up, what happens when we have 5? All right, so again, with 5 electron regions, we are going to be taking advantage of that forward and backward, or in front of the plane, behind the plane space. And so the shape that we're going to be creating actually makes these 2 pyramids, okay? And so the name of this is going to be trigonal indicating that there's a triangle base, bi, meaning there's 2, pyramidal. So there's going to be 2 pyramids that we're going to be creating here. Now, when it comes to the position of where these atoms are going to be located, we're going to have 2 different positions we're going to be thinking about. Electron atoms can be placed in this molecule either in the axial position, meaning top and bottom, or in the equatorial. And that name equatorial should sound familiar, like equator, meaning the halfway perpendicular to that axial position. And so we'll end up with 3 regions or 3 atoms in the equatorial position to make that triangle base. And then the other two atoms are going to be placed axial, one on the top and one on the bottom. And so again, that shape is called trigonal bipyramidal. And so again, if we put a representative atom here, you would have one on the top, one on the bottom. So those are your axial. Then you have some in the equatorial position, like so. And again, you see this triangle base that's being created there. Okay. And you can see the two pyramids, top and bottom. And so when we're drawing these, again, we would show the axial with straight lines and one of those with a straight line indicating that it's in the same plane. And then we would have a wedge line, like it's coming out at us, and then a dash line, like it's going away from us, to create that trigonal bipyramidal, or those triangle base with the two pyramids. Okay. And bond angles, what we're looking at here from the axial to equatorial position would be 90 degrees. From axial to axial would be 180. And from equatorial to equatorial, it's again a pyramid, so that would be 120. Okay. All right, and then you can see an example here shown for you with PCl5. Again, draw that Lewis structure first if it's not present for you. Then you count the lone pairs and the bonding regions only on the central atom. So here we would have 0 lone pairs, 5 bonding regions. So that means automatically with a total of 5, the shape we know we're creating is trigonal bipyramidal. Again, these are your electron geometries, and you would show your central atom here, your phosphorus, 1 in the axial or 2 in the axial, and then 3 in your equatorial positions. Okay. Again, the shape will be the same anytime you have something with 5 electron regions. And again, here you can see that's kind of space filling model for you. All right, and then the last type of electron geometry that you can have is when we're dealing with 6 electron regions. Now, the name is going to throw you off because likely if you think 6, you're probably thinking the name should start with like hexa or something like that. However, the shape that these atoms are going to make is actually something that's called an octahedron, or an 8-sided figure. And so the name doesn't necessarily correlate with the number that you're thinking, but you have to think about the shape that you're creating. And so much like with the trigonal bipyramidal, we are going to take advantage of that axial space, top and bottom, and the equatorial space around that middle section. But now we'll have 2 in the axial, 4 in the equatorial, making kind of a square base. And so this is what's known as octahedral. Now, because we are making a square base, the bonding angle between each of these is going to be 90 degrees. Making that square base, all the bonding angles are going to be at 90 degrees there, okay? So you can see here this shape, and remember I told you you're making an 8-sided figure. And so in your central atom would be here, you would have 2 in the axial position, and then you end up with 4 in this equatorial position. Again, we would indicate these with in the plane designators, and then these 2 actually are coming out at you and 2 that are going away from you, okay? And you can see an example here with SF6. Again, remember, we're counting only the lone pairs and the bonding regions found on the central atom. And so we would have 0 lone pairs, 6 bonding regions. And so with that, if we have that, then we would know that the total is 6 electron regions. So the shape we're making is an octahedral geometry. And here you can see that space filling model and the ball and stick model. I hope this video helped you guys understand different electron geometries. Remember, there's only 5 options that you can have. When it's 2 electron regions, linear, 3 electron regions, trigonal planar, 4 electron regions, tetrahedral, 5 electron regions, trigonal bipyramidal, and 6 electron regions, octahedral. Make sure you guys come back to the next video where I'll be discussing the different molecular geometries that you can have, because there will be some additional ones. Make sure you guys like, comment, and subscribe, and let me know what other content you would like to see. See you guys in future videos. Have a great day. Talk to you soon. Bye-bye.